All right. What questions do we have to start things off? Birthday. I've had many birthdays where I've had class. Let's see. I don't remember if I had that one this year or not. Anyways, talking about the graph matrix later tonight. Yeah, we'll go over program 3 tonight as well. The graph list, of course. Yeah, we'll talk about the height. Let's see. Where's that? Yeah, we can go over practice tests today too. Where is our practices? There we are. All right, still have a couple weeks before we go have our trees test. Let's see. Now let's do all the tree stuff first, shall we? All right, program 3. So finding the height of a tree. You're going to want to use a recursive function. All right, so say we're trying to find the height of this tree. All right, so we have the root. We start off where and come here and ask what's the height. All right, so the height of a tree is going to be based off of the longest leg of the subtrees plus 1 for itself. All right, so we'll make a recursive call. The left subtree and a recursive call on the right subtree and ask them how tall each one is. So we come down here, it's going to ask what's the height of my subtree. It's going to make the recursive calls to the subtrees, which would then return back -1. Max -1 plus 1. All right, so -1 plus 1 means the height of this subtree is 0. All right, so tree that has a single node in it equals a height of 0. So 0 is the response that comes back from this subtree. -1 is the result of this subtree that comes back. Max of 0, -1, 0. 0 plus 1 gives us a height of 1 for the entire subtree. Yeah, there would be two recursive calls. Sample input and output. You mean like uh we have the modules page that talks about trees. And we should have an image here with the various heights in it. Here we are. All right, so given let's add our background. Right, so we have a tree here. So if you just build a one node tree, your height's gonna come back as 0. Build a two node tree, doesn't matter which way it is, right? You're gonna have a height back of 1. All right, it doesn't mention the height here. Let's see. Child depth of 1, height, tree, 1. All right, lowest node depth at 1 here, and then we have 2. 3 levels, height 2. The tree is 2. You talking about sample input output for the program itself? I see, I see. Okay. Yep. In fact, let me do that. Yeah, over here, I'll make a note here. I'll actually create an item so you can submit and test your program to see if it works for the smaller subsets. All right. Yeah, so the finding the height is recursive. Mo Many of the functions would need to be recursive for this, right? All the traversals are recursive. Building the tree does not need to be recursive because any given individual add to the tree will only be going down a specific branch. So that doesn't need to be recursive, right? Tree has to be recursive, right? It's even called out in here. Number of leaves, also recursive. It's the same idea. Right? You just need to establish the base case. Right, so got a tree here. Right, how many leaves are in this entire tree? So it's going to ask how many leaves for the left subtree, how many leaves for the right subtree. Eventually we'll get down to a base case, right? So this is going to say I don't have any. So there's 0 leaves in that subtree because it's empty. And then we'll get to a subtree that has both null left and right pointers. So this, you can see there's 1 leaf in this tree and that returns it back. Right, and you just add together the 0 that came back from the left with the 1 that came back on the right. So we come back with one leaf in this tree. Right, so if we have a bigger tree, this tree should say there's 1 leaf. This tree should say there's 1. And then we have 1 plus 1 for the whole tree. All right, so it's very, very, very simple. Once you have basically one of the traversal patterns down, you can follow the same pattern, except we're just doing a little bit different mechanic with how we're determining what the base case is for the recursion. Right? Generally, we're hitting a leaf or we're hitting a dead branch to stop the recursion. And once that's done, what value should come back out from that base case? And this is the particular base case. So you have 2 base cases: one where you hit a leaf node and returns back I'm a leaf node, or you hit a dead branch and it says I have no leaves because I'm not a tree. Right? Search does not need to be recursive. That can just go down a branch. Lowest weight, right? It's going to have to be basically a traversal. Right? Do a traversal and grab the values, basically grab the min. Do the same thing here, right? Because the lowest weight could be anywhere in the tree because we are not keyed off the weights. So you can ask what's the smallest of each subtree. And then in turn, we'll do the same recursion, going out and return back the smallest. So the 2 comes back out of here. All right, 1 comes back out of here. And it's the min of the 2, the 1 plus the node itself. Then the smallest value of those 3 shoots back up. All right, and number 9 would also not be recursive. Or you could do it recursively, but it wouldn't go through more than just a branch. Any other questions about program 3? All right. Did we get to our complete bipartite? Yeah, yes, we did. Okay. Any questions about our graph shapes? All right, let's combine various shapes with the matrices that they would have. All right, so we go steal the image. All right, so we'll need 3. All right, so whatever the labels are in here, I guess we'll add the labels at this point. All right, so alphabetical order. When we're building our matrix, right? A goes to B, A goes to B, and C goes to A goes to C. B goes to A and C goes to A and B. All right, so every single row or column, however you want to look at it, remember the source vertex is on the left. A has 2 neighbors, B has 2 neighbors, C has 2 neighbors. And we'll have the same pattern going on for each of these, right? D, E, F, and G. Right, so we do this alphabetic order, that way the same image would produce the same graph all circumstances. So we got E and G, 2 neighbors, and we have F as E and G as well. F, E, and G, and F as E and G. All right, so 2, 4, 6, 8, right? We have 4 edges in our graph. Since it's a simple graph, we'll have 4 vertices, excuse me, 4 indices in the on state. And we got G, H, I, K. All right, so G has K and H, K and H. Then H, G and I. Right, this should just be the 2 for each one of these. I, J, and H. And J is I and K. I, K, and K is GJ. J, G, J. Right, so you'll definitely see a pattern here. We'll have 2 diagonals going along the center mirror. If things are in alphabetical order as they're built, so that's not necessarily going to be the case for all cycle graphs, but 2 per. But the fact that I built my cycles alphabetical order and laid them out here in alphabetical order, same trend will apply if I rearranged the vertices. That wouldn't necessarily hold. All right, so let's demonstrate that before we go too far into that. right? With a similar graph. Right, so we got a C5 here, and we'll just swap. What was that? H and J. So it's not quite. Let's see. All right, let's get our scale in place here. All right, so we'll label the vertices the same, but I changed who our neighbors were. So let's clear this out and make sure we don't make any mistakes. G has J and K. All right, J and K. J has GI, or I guess alphabetical order. H has IK. I has HJ. And next up, J has IG, GI. And lastly, I have K for GH. K, G, and H. Right, so two vertices in a row. So the pattern might arise depending on how we label the order of things. But the degree of 2 for every vertex in the graph will be the key thing. So if I give you the reverse, say I give you the matrix or the list, I ask you what shape is that graph? If there is one, the degree will lend the answer to that. All right, and then our adjacency list. Very much the same idea. All right, we have 5 vertices in the graph. So the array will have 5. And each list depend on the connectivity. Since we have a cycle graph, every single one will have 2 entries. Just gonna go get my drawing. So we can build it accordingly. All right. Okay. Again, the list will also be in alphabetical order. The lists will also be in alphabetical order. H, I, J, K. Double check my mind, make sure I'm getting things right here. Where's I? H and J. Who J has G and I. And K is GH. All right, so I'll do the same thing here. Ask what shape graph is this? This would be a cycle graph. And quickest check, they're all of degree 2. If they're not all degree 2, then would possibly be a cycle graph. So you can check out the options. let's call that or C for our cycle graph. Questions about our cycle graphs? There it goes. I thought I copied the wrong thing for a second there. Seems we have no questions. We'll keep on building. All right, our star graph. We have some sort of central vertex. And some sort of label. And look at that. We managed to stay within base 16. All right, so our star graph with all of one vertex. All right, one vertex. And no connectivity because it's just a star. One doesn't connect to anything. All right, 2 connects to 3, and 3 connects to 2. All right, doesn't really much, as we mentioned last time, seem like a star graph. Really, I think S4 is our first one that actually becomes anything that looks like a star, but the other ones hold to the definition of the type. Right, so who's our central? 5 is our central. So 5 will connect to everything. And that's it, right? So everyone has a degree of 1. So each row, right, in all these examples, each row has a degree of 1, with the exception of the central vertex, which pretty much impossible to tell just by looking at the second matrix, who's quote unquote the central vertex. Which is why I kind of balk at calling those stars, but that's how things work. So I got S4 here. C, D, E, and F. And D is our central vertex. So D will connect to everyone except for itself. All right, and again, remember, if I don't put a number in there, that means just 0. The void is 0. So everyone has a degree of 1, except for that central vertex. And what we got here? Start at 7. All right. And 8 is our center. So 8 connects to everyone, except for itself. And if we look at the list for our last one here, you'll see there's not a whole lot difference in the appearance. All right, alphabetical order for everything, or numeric order as it may be, since we're using base 16 numbers. All right, 7 connects to 8, as does everyone else. But then we'll need to expand things. Didn't grab my edge. Okay. Right, so very little. Totally missed those arrows there. Right, so there's a similar look and feel. We got one line there versus one line here. A lot of data points. Otherwise, just the one tick in the other rows. How are we doing with the matrix and list? Mist. Yeah, just smash the words together, make new words, or other words as it may happen to be. No questions at the moment. Yeah. Yes, we can take a little tangent there. I don't think I ever played that one. What would the code look like for them? Yeah, well, we can do some code tonight on these. Right, we've got the lab to talk about anyways, and we have the graphless one that's due this week. Not that you're submitting it, but we'll definitely get into some code. Right, I'll assume we can draw the other shapes and their corresponding matrices and fun stuff there. Okay. All right, let's do the code now. Let's talk about graph matrix. Uh, Interesting. I don't know why that's showing already, but anyways. Da, da, da. Okay. So constructor to build our array. All right, so they'll get us our matrix. Let's see now. String. All right. All right. We will index. There's lots of ways to do various things here. So the way I'm doing it's not necessarily the only way to do things. Labels, so I equals label. Right, so we'll add a linear search to get our index from the label or the labels that are in these. I remember what I say for the labels. I say do the constructors do it separately. Number of points, labels, non-specific, so we can do it whichever we want. Eh. Just do over here then. Probably nice array function to copy these, but I already have a loop. Just use that loop. Labels sub I equals vertices sub I. Number of vertices. All right, we'll have to test that, make sure all my code's bug free. At some way or another, we need to get our indices. And then we will just set our edge to on sort of thing. And we more or less needed a print function, right? So row less than size, row plus plus. And we'll just spit out our source vertex. What I call them, labels. Sub row. Labels column. I forget what I said the sample output should be, but we'll give that a whirl and see how that works. All right. I guess I should call the build part first. Big as the matrix. Labels. Mhm. Yeah, I keep trying to use IntelliSense auto-complete my for loop and it's not working. Whoa, froze. Labels sub-I. All right, and let's build our matrix. All right. Ask for a source. And then ask for a destination. And then we will add the edge. And then we will print to make sure things are working. And let's see what bugs we have. Yes, writing C++. Yeah, that silly semicolon over there. All right. What else did I not like? Labels. Typos. All right. Start small. A, B, B, C, C, D, whatever labels are going to be. A, B, C, D. And it seems oh, forgot some white space. That's just terrible. A, B will go to A, B. Why not? And C, D goes to A, B. All right, -1, -1. Kind of missing an earlier break, but that's the idea. Some people might have just done a single string or a single character array for all the labels and then single character names for labels. That's all good. And that's the question for the graph list lab. Would we redo what you're doing but use nodes? Yeah, so right, obviously the main function can pretty much stay the same, just change the name of the class from the matrix class to your graph class, right? Make it a little bit more agnostic to what the underlying structure is, but you'll need an array of linked lists. So you want to create a node class, a list class, and inside the matrix, right, instead of being an integer array, two-dimensional integer array, we would have just a linked list array. So the other parts could stick around the size, the labels. Different ways you can do the labels, right? Because the label could be, you can just store the label on the node itself. So the node can have a label field. So when you look, so the very first entry, where you can have that in the list class as well, where we want to store the label for vertices. There's lots of different ways you might want to do that. Probably in the list class, the best place for the label, because that label represents that as the source vertex, and then each node, the label in the nodes would be the destination vertices. Oh, all new Chromebook Plus. Woohoo. All right. Yeah, we will talk. So, right. So that was the matrix. Any questions on the matrix? Right, if you did it as a simple graph, right? What turns this into being a simple graph? Pretty much copy this line and reverse these indices, and now it's a simple graph. Each edge goes both ways. Printing it out, we should probably adjust the printing so that it, let's see, row +1. That should take care of that. All right, so 4 matrices. All right, A goes to B, and B goes to C, and -1, break out of the loop. All right, so we have A to B and B to C. All right, and it's a simple graph, so we wouldn't list out the other directions. So there's not much of a difference code-wise between for the implementation of the one versus the other. Either which way is perfectly fine for the lab. Okay, so for the list, right, if we have a node class, where we could have a label, and we could have node star next. And we can have a list class. Right, you can have a label. And you can have a node star head. All right, and then we would need an add function. Basically takes the destination node. Just keep in mind that this is a sorted list. So when we add the node, it's not just pop it at the front. If the node's name is lower than, the head goes in front of the head. If it's higher than the head, goes after the head, goes wherever it would be in the list. And then we'd have our graph class. All right, and it would have list array for all the various nodes. Right, it has an add function. Source and destination. All right, here we just need to figure out which list to call the add function on. If the source is the first vertex in the list, then we call add on that array sub 0. If it's the second, right, array sub 1, so on and so forth, and we just call the underlying add function with the destination, and it adds it into there. All right, and then print function. All right, so you'd have a print up here, and then you would have a print down here. All right, print here, it simply just iterates through the array, calling the prints for the lists. And this just simple temp pointer starts at head, prints out the node, and iterates down until it hits null and keeps on printing as it goes. All right, so there's isn't really much different code-wise than what we've been doing with all our linked lists. It's just a matter of creating now an array of them and working with a collection of lists all at once. Right, and your graph class will do the management of the array. Right, assuming you're using classes, you want to use classes. If you're not comfortable using classes, now's a good time to start getting comfortable because OP is going to account for the vast majority of new and ongoing software development out in the wild. Assuming you plan on becoming programmers. And if you're going to be going networking or a database or something like that, yeah, object-oriented programming is not as particularly relevant over there as it would be for application development. Right. Let's see. Right. So your main function pretty much be the same. Ah, Weighted graph though. All right, so weights. Some of the other graph types that we haven't talked about yet, which we will be talking about tonight. So to make this support a weighted graph, we would add a weight into the node. That'd be the weight and how much it costs to get to that node from our source vertex. So let's continue on. Right, we started talking about some of our graph types. Graph types. Right, we have simple and directed graphs. Pretty much all of our additional graph types are going to be based off of either it's going to be a simple graph or it is going to be a directed graph. And so these are our two foundations. But we're going to expand on these. All right, a weighted graph. Post the link. Get some extra stars over there for some reason. An extra colon. I probably messed it all up. Post it again. All right, so a weighted graph is going to be a graph that has a cost, label, or weight associated with the edges in the graph. Right, so that value may represent a transition cost, distance, or anything else for that matter. So let's draw a weighted graph. And is a simple graph. Its foundations, all these edges can be bidirectional. If we put arrowheads on them, then that means we're associating some additional weight to go along with, or a direction to go along with the weights in the graph. So there's our first weighted graph, right? A to B, B to C. A to B has the cost of 2, and B to C has the cost of 5. I could also have a directed weighted graph. Let's add in some arrowheads here. And get the screen to work with me here. That's interesting. Doesn't resize. Okay. Until I reopen it. Oh, no, it's just I made it too big. All right. All right, so if We want to show the corresponding matrices. Right, A goes to B, so now instead of it just being a Boolean, we're gonna have to change it to integer. Which is part of the reason why I start off with integer when talking about BC5 matrix lab. All right, so and then we have our matrix for directed one. A goes to B, but B does not go to A, and B does not go to C. All right, so there's not much of a change. Go from just a simple graph or a directed graph to a weighted graph or directed weighted graph or weighted directed graph, whichever way you want to phrase that. Other than we have an additional data point to now track. For the matrix, right, instead of just setting the value to 1, we would need to pass the weight in. Right, so if we were to go update, we have this support weight. I'll add a weight in here. And then I'll capitalize it. Source, destination, and the weight. And update our add edge. And instead of just being ones, now it's our weights inside the matrix. All right, so then we can print out a weight for our data points. And make this a not equal 0. Array, row, column. Right. Didn't quite type the whole word. Right, 3 elements, A, B, C. A, B, 3. Apparently I'm missing a CN statement. A goes to B for 2, whatever. I forgot my closing bracket. And B goes to C for 5 type thing. And now we have a weighted graph. All right, so it's not a whole lot changing. We're just going to be adding layers of detail that the graph can support. That sample code available on Canvas. I can share the link. Next graph type will be a multi-graph. Let's see, graph type, weighted graph, graph type, multi-graph. Oh, I did forget to do the adjacency list over here, so let me get the list first. All right, so we have our 3 nodes. We had A, B, and C, A, B, C. I believe A went to B, a second data point of 2. And B went to C for a data point of 5. And the reverse over here. C went to B for 5. And then we just need my other nodes. Once I go look at what they were. All right, so A, B for 2, B, C for 5. All right, make sure I got that right. So my B node needs to get added in here. So this needs to slide to the side. B goes to A for 2. Yeah, we need to maintain these in alphabetical order. And there we go. All right. So there's our list. We have 4 nodes in here because there are 2 edges, and it's a simple graph, so we'll have 4 nodes represent the bidirectionality of things. And then when we transform this to be our directed, right, A goes to B and C goes to B. So we'll just delete. All right, we have 2 edges in the graph. And since it's a directed graph, we'll only have the 2 nodes in our directed graph. And it's like before, we're just adding an extra data point. So we ask, how much does it cost to get to B and where's B a neighbor? We go to the A list, and then we look at that list and see if B exists in the list, and if it does, what the cost is. All right, so we passed in cost to get to B, and the result would be 2 for that function, or -1 if A could not get you to B. All right, so what's the cost for A to get to C? I'll come back and say just back -1. No such edge exists. And most commonly, graphs will have non-negative weights for their edges. It's not necessarily always the case, but it's typically going to be the case. All right, a multigraph. Did I post a link for this one already? ME, no, I did not. All right, multigraph. It's a graph that will allow for multiple edges between a pair of vertices, right? Again, if we don't specify, it's a simple multigraph, right? But we can have a simple multigraph or a directed multigraph, just multiple edges between a pair of vertices. So let's draw. Multiple edges between a pair of vertices. All right, 2 edges. Not going to be very common that we would just have 2 edges all by itself without there being weights associated with it, but that would be a weighted multigraph. So we gotta wait till we get there. And so that's a multigraph. If we want to make it a directed, Right, so we've got our simple here. And then we will make this one a directed. When I make this directed, they both need to have the same source and destination. Otherwise, if I were to reverse one of the arrows, that would just be a directed graph. Really, it'd be a simple graph. I just drew each edge independently, but since it goes both ways, that's a little bit of a gray zone there for the way we're drawing it, how that would play out. Right, so we have my graph definition here is my set of vertices A and B. I have my set of edges. Right, and I have AB for the first one. So that was graph one, which is our simple graph. And we have graph two. Direct graph, set of vertices is the same, A and B. Set of edges, AB, AB. Right, exact same thing as we had before, except that we have to call out the way this one is, that it is a direct graph to know it's a direct graph versus a simple graph. Only way that we'll know from the set notation that it's a directed graph for sure is if we have AB and then BA type thing where we have source, destination, destination, source in the list somewhere, which means those edges are not the same edge, which means it has to be a directed graph. Because in a simple graph, we would not list out BA if we have AB. And on that thread, unless we are doing things in alphabetical pattern here, right? Because when we list, if we were to build out, say we had the matrix or the list, right? All of our code algorithms that we're going to go through once we start getting those on the graphs, we're going to be using the underlying matrix or list to run through, and those exist in an alphabetical fashion. So if we're going to list out edges, they will be listed out in an alphabetical pattern there as well. Let's see. All right, so let's do some more. Well, let's get our matrices and lists first. It's going to look just like a weighted graph, except instead of these being weights, it's just the number of edges. All right, so it looks like a weighted graph, but it's a count of the edges between a pair of vertices. Let me go steal images. And well, let me select them both. All right, 2 copies. Just have to change one number and we're good to go. All right, so there are 2 ways for A to get to B, 2 ways for B to get to A, and 2 ways for B to get to C. So we adjust that number. 2 ways for C to get to B. And this one, A gets to B in 2 ways. Oh, and of course, there's no C here. Guess I do need to get rid of the C node. Trying to make the graph bigger than it was. All right, so A goes to B, and the two ways. B goes to A 2 ways. And then A goes to B 2 ways, and B doesn't have any outbound edges. Right, so B has no outbound edges. Everybody. going towards B, which is just from A. Trying to make my arrows a little bit better looking. Anybody lost? Anybody confused? Or everyone's just waiting for the recording, rewatch it back 10 times. Two-thirds or 2 out of 3, one or the other. Okay, let's make more involved multigraph. It's not necessarily every edge. Will dictate multiple edges. Might have a pair of vertices where there's just one. Might have pairs of vertices where there are two. And a number in between. Right. Kind of looks like modern art there. So it's a simple multigraph. Right. The names of the vertices aren't important. And if we come along and just start adding arrowheads somewhere, I'll add a few so they're easier to spot. Right, arrowheads, little tiny arrowheads. Now it's directed. All right, so a weighted multigraph is going to be where we start to have the most common application, where you're getting directions or air flights, right? Which is typically going to be a directed multigraph because when you're, well, so one way directed multigraph, no, I mean, yeah, round trip even would be a weighted multigraph as well. Let's get that one going. So now we're gonna composite those two together. I'll go steal this image. Again, it might be simple or directed. So now we'll have a weighted, directed multigraph. So now we'll have costs. All right, so might be $100. LAX, Houston, add whatever New Orleans is in New York. And it's quite possible this is a small airline, so they don't actually have any direct flights from LAX to Denver, Denver to New York, right? But their hub is Houston. So what we'll have different price points. You might find out there's this red-eye flight on the way back from Houston for $25. And they have a special airfare rate, $79 Houston going here and there. I'll just use $100 as my base airfare for any of these particular legs of the trip. But from New Orleans, it's a one-way flight because otherwise you got more people trying to go to New York than they have go from New York to New Orleans. Most people tend to go from Houston to New Orleans, whatever the data may be for that traffic. So this is the kind of data that you would typically find for airfares, or this is how we would model that data, right? Multiple flights from LAX to Houston on any given day. Right? So in addition to just the cost of the flight, we'll have additional data points. We'll have what's the flight duration? What's the type of plane that we expect to be using? Right? Is it 737, 747 is a little two propeller job because it's a really short flight. Yeah. They might be short, but they're still long, even though the distance isn't great. Um, all right, so here's where things get more complex for the element type. And so the element type in our graph is going to have to go beyond an integer. All right, so using matrix to encode this in memory will require object type for elements. And so whatever you want to call a trip class, and it'll have double for the airfare, right? Double for the miles, etc. as the type. Yeah, so without the arrow, there's a flight that goes both from LAX to Houston and Houston to LAX for $100. If we're only looking at the rates, it'll be good enough. But in a more practical scenario, the return flight's not going to have the same time or flight number and all that other stuff. So it's going to have to be purely directed with that set of data because there will be different data points. So I can't use the same object for both directions. I'll have to be two instances of that object in each element because the additional data will not be the same. But typically, if we're going to be running an algorithm on this, we won't necessarily need all those data points because we're trying to minimize what's the cheapest way to get from LAX to New York, regardless of the number of layovers. Right? It might be you go LAX to Houston, to Denver, to New Orleans, then to New York. Right? This airfare over here from Houston, New York is $1,000. You're like, yeah, I'll spend an hour in Houston, go to Denver, spend an hour there, go to New Orleans, spend an hour there, and then you go to New York instead of flying direct because whew, $300 is a lot less than $1,000. And so it just depends. So typically, when we'll run an algorithm on here, it's most likely going to be a path algorithm, shortest cost path algorithm. We don't care what the times are as much, but there's other ways to sort. If you go to the travel air site, you can sort by travel time. What's the shortest travel time? And usually the direct flight should come up first. And then you'll compare that. All right, direct flight, $1,000, 4 hours. And what we just talked about here, okay, 2 stops, $500, 12 hours, right? And so depends on how much you value your time, 8 hours of time, and living on airport food or whatever you pack along with you for that duration. All right, so we have a composite. We have the characteristics of weight on the edges, multiple edges being allowed between pairs of vertices and one or more edges in the graph having a direction, right? It's the weighted directed multigraph. Just simply applying the characteristic sets of those three types of graphs together. We're going to do any algorithms on this in this class. Weighted graphs. We'll use Dijkstra for weighted graphs for a single point shortest path. And that's our weighted multigraph. Just have pseudograph left. Double check my notes. And this is one of the areas where some authors have slightly different variations on things. All right. So to click pseudograph and allow single node loops. So we can have an edge AA RBB, for example. Finite state machines or finite state automatas. We've taken the computer math class already. Then this is what you were talking about. You have multiple nodes. And the typical example for a finite state machine would be like a vending machine. All right, see if I can get my curve connector going on here. Interesting. Why didn't you attach? Go away. All right. Oh, work with me here. Okay. So we'll have an edge. If I can get it to grab, where's my anchors? Close enough. Hey, we got one. One in the right spot. So the edge goes from the same vertex to itself. Right, so say we have a vending machine that takes dimes and nickels. All right, very, very old style vending machine where you have to build out appropriate circuitry. Or to do what it's going to do. And get that in the wrong direction. Well, that's interesting. Right, so usually with this finite state machine, you'll have a few buttons. You have a button that says vend, right? So the machine has all of one product. Bottles of Coca-Cola or whatever, and it costs 15 cents. So you need to get to 15 cents. We're going to ignore the case where they put another dime in beyond, but we would want to account for that. So finite state machine, right? Basically, this is a program. This just be the amount money in variable. So if you put 5 cents in to the machine, that'll take you from one state to the next. If you attempt to vend from that state, it will not advance you in the machine because you don't have enough money in the machine for it to do anything. It might emit an output message saying that that's not a valid option. And this one could be two states, right? You try to vend or put in 10 cents. The machine may not have the ability to issue change. So it will just not accept 10 cents machine. Then it'll spit that coin back out because it's not an acceptable coin. All right, you toss a penny in, same thing. Penny just spins you right back to where you are. And they call it a pseudograph. Can that make sense? All right, so it's this particular characteristic that we have here at the top. That is what is making us a pseudograph. And these edges are effectively now directed, undirected. It doesn't really much matter. It's a single node loop, right? Because if we were to list out this graph, the notation, right? So we have our graph, we have our set of vertices. S0, S5, S10, and S15. And we have our set of edges, right? SO, SO. And we have SO, S5 with 0.05 cent weight there. That's an O, not a 0. Let's get that to be a 0. All right. S0 can go to S10. We have a 10 cent weight on that edge, et cetera, et cetera. All right, SO. Is this the directed edge or an undirected edge? You can flip them around and it's still the same thing. For the purposes of this class, it doesn't matter. We're not trying to get too deep into all the various graph types that there are. Right, because there's a bunch of them. Do like a claw graph. Claw graph. Here we go. Here's go to Math World. Math World's actually not too bad for data structures. We have some stuff in here. But there are a lot of different types of graphs. Right. House graph. We'll actually look at the house graph later. Because there's a game there, but there's all kinds of different graphs out there for the shapes, different types of shapes of graph. But there's only so much time in the day. So I did say I will post a link to the other shaped graphs. So I will remember to do that tonight. Otherwise, any questions about the pseudograph at the moment? All right, let's take a 5-minute break and we shall continue on. And repeat what GVE means. Oh, graph vertices. You can type it. Edges. Any questions at the moment? All right, let's get into some algorithms here. Get my mouse to work. For a weighted graph, no. What I already had, remember here we did earlier, we just passed the weight along and set that as the value instead of 1. All right, new doc. All right, so traversing a graph. Traversing a graph. Right, either to find a specific node or to visit each and every node in the graph. All right, so we have two options. We'll discuss depth first search and breadth first search. Giving a starting vertex will work our way to all the other vertices. Right, so they are called searches. So often you'll be searching for yourself to detect if there's a cycle within the graph, because some algorithms don't like there to be cycles. But right, so our algorithm here. All right, so we'll mark the starting vertex. Go to the first neighbor of the vertex we're at that hasn't been marked, aka visited. Repeat, going to neighbors until there are no neighbors that we haven't been to yet. Backtrack when we've run out of neighbors at the current vertex to the previous vertex. And then repeat checking for neighbors. Is there a shortcut key for this? And then we'll keep backtracking as needed. All right, let's build a graph. All right, we'll have a fair number of vertices here, the fair number of edges as well. And we'll leave them A, B, C, D across the top, E, F, G, and H on the bottom. Generally, we'll only concern ourselves with simple graph because we don't generally care. Generally care that, or most algorithms aren't particularly interested in directed graphs, but you can assume simple graphs to start. All right. Okay, so starting at A. A has three options for where to go first. We can choose, well, we need to choose between B, E, and F. So before we start running through this, the computer is not running the algorithm on an image, right? This is just a way for us to visualize the graph. The computer is running this on a matrix. So we have 8 vertices in here, so big matrix. A, B, C, D, E, F, G, H. All right, so A goes to B, E, F, B, E, and F. B goes to A, C, F, G, C, F, G, C, B, D, G, B, D, G, D goes to C, H, and E goes to A, F goes to A, B, G goes to B, C, and H goes to D. All right, so the algorithm is starting at A. It's going to say, who can I get to that we haven't been to, right? So A has been marked. All right, so we'll go ahead and put a little stamp on A saying we're not going to go to A from somewhere else because we've already been there. Going to someone we've already been to is just going to create a loop. And you can't get very far if you're stuck in a loop. Right, so the underlying data structure is going to be consulted. The first vertex that shows up is B. So that's who we're going to go to. And so A goes to B. B is the first neighbor that is unvisited. All right, so go ahead and mark B. It's like my stamp has gone off kilter there. So we're now at B. So now from B. Our options are whatever's in this list. Right, so we have A, C, F, and G. A is already marked. Right, so our real options are going to be C, F, and G. C is first in the list. So B will go to C. All right, so we are moving along, building up a path, and marking the vertices as we get there. All right, so from C, go look at the row. Options are B, D, and G. All right, B is marked. So that means D is up first. So we have C going to D. All right. Let's move this to the side. All right, so we're going along here. We haven't hit a dead end yet, so we can keep on moving. From D. All right, D has two options, C and H. C or H. C is marked, leaving H as the only option. All right, so D goes to H. Got my arrows. We went to D. We marked it. And now we've just gone to H. We've hit our first dead end. All right, so at H, there are no more neighbors that are unvisited. So we'll backtrack to D. So we're back at D. So working our way back to the previous place, looking for additional neighbors. There aren't any here. So same thing, repeat this statement, and we'll backtrack again to C. And so we're back at C. Now we have G is the only unvisited neighbor. All right, so from C, we will go to G. Mark it. So we don't consider it as a path again. G is a dead end. Dead end. Back to C. So backtrack again. Nope, that's not quite what I was trying to do. Let's try that again. All right, so we're back at C again. And now this is a dead end. So go back to B. All right, the net result of this will be effectively a tree. Ugh, keep clicking on the wrong arrow. Back to B. All right, so back at B, we have F to go to. So B goes to F. Moving forward direction, marking it. is somewhere we've been. Right, so we're at F. At F, we have a dead end. So we'll go back to B. Right. And then we'll go back to A from there. Right. Back at B, it's a dead end now. So we'll back track to A. Back at A. We have E as an option, so A goes to E. A goes to E, that'll be a dead end. So we'll backtrack after we stamp it as now a visited vertex. All right, so add E, dead end, back to A, add A, and no further paths to build. So interesting the way that there's a screen grab of that over there. Anyways, well, red doesn't look so red anymore. That's probably because of the dark filter. All right, so some edges, as you can see, weren't utilized in our depth first traversal. We just keep going as far as we can go. Again, when we have a choice to make on which branch to follow, the underlying data structure would be used to make that selection. So it is not at all arbitrary. It's based on the underlying data structure. The underlying data structure is stored in alphabetical order, so the order that we do things will be alphabetically. We didn't take the slanted paths because that just happened to be the label, the values of the labels. If I were to switch B and F, right, so let's do this again, right? The fact that the edge is at an angle is just happenstance of the way that the drawing was made. So if this becomes F and this becomes B, and we do a traversal here, right? Assuming we start at A, we have three options, three choices to take, and the matrix or list says that this is our first choice because B is before E and F in the list. B has one choice from here, and then we'll go this way, and then this way, and then this way, and we'll work our way back. We'll find a new neighbor, work our way back. Right, so we're not necessarily taking the shortest ways back, but C might have had additional neighbors over here that we would wanted to go to if there were any. Right, there could have been Q, P, or whatever off on that edge. Work our way back, and then come over to E because E is not yet been visited. Right, so when we're making a choice, we're going to underlying data structure and then pulling the first vertex from that list that we can go to. We've already been there, then we'll skip it and go to the next one. All right, if we do the same thing again, starting somewhere else, oops, killed my image. All right, so this time starting at B, and we'll start at F. All right, so F will be our starting vertex. Goes to A, then B, and then we will backtrack and do dashed lines. This time around, into E, and we'll backtrack. Go back to where we started. We have B, C, and G. So we'll go to B, backtrack, C, D, H, backtrack, and backtrack to where we started. All right. Breadth first search. And this algorithm make use of a queue to keep track of neighbors, right? Neighbors being adjacent nodes that we still want to visit. All right, so step one, NQ, NQ, starting vertex, repeatedly DQ from the vertex, and then we'll NQ the unknown vertices, marking them as known as we NQ them. All right, so for NQ vertex is marked as known. So using the same underlying let's go back to the first one. We don't even really need the drawing. We have the matrix. All right, so starting at A, we'll start at H. Where we start is pretty much arbitrary of a Q. All right, so H. My Q will NQH. And we'll go ahead and DQ. Typically we'll output H at this point in time. And we're going to NQ H's neighbors. All right, so we go to our list here and we see that D is its only neighbor, so that's all we have on our list. DQ, was that D? Outputting D. NQD's neighbors. All right, so we'll go with D's list. D has two neighbors, C and H, but we've already done H, and we don't want loops. So we will only NQC. All right, DQ. Output C. And we'll NQ C's neighbors. All right, C has three items, B, D, and G. D has already been done, so only B and G will enter the queue. All right, so from C has three neighbors. B we've not been to. G we've not been to, but D we have, right? It's been marked as someone to ignore. Or if we want, we could just be stamping things along here, right? H, someone we don't want to consider anymore. So we got N queued, same thing with D. Same thing with C. Okay, so we just now queued B and G. So B and G are no longer relevant. DQ gives us B, output B, and NQ, B's neighbors. So our Q still has G on it. So B, B. Oh, well, actually, that kind of works. All right, so B has A and F as columns that are not marked out. So A and F will get NQ'd, and A and F are no longer relevant, right? Only E as our unknown vertex in our graph. And G doesn't have adjacency there, so that will not. DQ. What was that? G. NQ's no neighbors. No neighbors. So our Q, just A and F. DQ gives us A. And we output output G, and we have no neighbors. Output A, and add E along there. All right, because if we go ahead and see if I can get my scroll. Ugh. All right, so when we look at A, the only vertex here that we care about is E. The other ones have already been visited, so we'll grab E, add that to the queue. Still had F on it. All right, DQ pulls off F, out it, no ads, and our Q is just E on it, so DQ, E, output E, no ads, my Q is now empty. All right, so let's get the drawing. So we started at H. With the breadth first search, we're going to stay as close to our source vertex as we can. So we went to D, right, which is 1 away. Then we went to C, 2 away. Then we went to B, it was 3 away. And then we jump over here. G is also 3 away. And we went to A at 4 away, F also at 4 away, and then E at 5 hops away. If we do that traversal, again, starting somewhere else. All right, we'll start at B because it's very highly connected. So we will stay near B longer. All right, so we go to A first. It was 1 away. Then we'll go to C, also 1 away. F, moves 1 away, and G, also 1 away. Now next up, A was hit first, so this was NQ'd. E was NQ'd, C was NQ'd, G was NQ'd. So we're going to go to E, 2 away. Then C was NQ'd. So this is 2 hops away, right? G gets DQ'd, but there's no one to NQ at that point. And then we have H at 3 away. And so if we label these let's see. We'll do 1.1. That's the first one we did. We had 1.2. 1.2. This was 1.3 and 1.4. And then we had 2.1 and let's see, 2.2, and there's only 1.3 away. So it tried to stay close to home. All 4 neighbors are visited first. Right? I'm searching for my lost cat. So I check all my neighbors' houses first. And then we start checking further and further away. Right? So we kind of do like a spiral pattern, trying to search the neighborhood, trying to find the lost cat. Because we expect our result to be closer to home than further away. Questions about breadth first search. All right. Now we're going to take that depth first search pattern, fold in Dijkstra's single point. Dijkstra's single point, shortest path. Toss the link in the chat. Go grab the Wikipedia link for this one. Okay. Before we get into Dijkstra, let's establish a class of algorithms. Greedy algorithms. A greedy algorithm, one that when presented a choice, it takes the most beneficial option available to it. All right, so Dijkstra's algorithm. Our objective is to find the shortest total path length from the source vertex to every other vertex in the graph. It is a greedy algorithm. What we're going to do is start building paths from the source vertex, building the shortest path that we can build amongst our options. All right, so this algorithm applies itself to weighted graphs where the weights are all non-negative. Negative weights would break the greedy nature of things. All right. Got a lovely graph over here. Might as well leverage it. We're going to need to add some weights. To make this applicable. All right, there's a nice edge. So A to B will be 1. A to E can be 4. A to F can be 2. Let's make that a 3. B to C be a 2. B to F be a 7. B to G will be a, yeah, I'll leave that as a 1. C to G be a 3. C to D leave as a 1. And D to H leave as a, make just as 2. It doesn't much matter. There's only one path to get to D and H anyways. My screenshot disappeared on me. All right. So we're going to build a table to track the algorithm's progress. Have vertices along the first column. Second column will be total path length. Uh, let's see, to the destination vertices, to the vertex, and if we know the vertex is in a path yet. Brain is feel like I need another column. We'll start with this. So what do we had here? 8. Distance known. All right, so we'll just put these in order. Doesn't much matter other than making things easier for us to find things. A, B, C, D, E, F, G, H. Too many rows. All right, so the distance. So we're going to use B. Just go around. Starting vertex is B. So initial state of the table, distance to get to B, and true. All right, this is where we started. So there's no shorter distance than being where you already are. From there, we're going to update the table. So for the current path that we're building, we'll look at the neighbors. And see who we can get to, and if getting there from the current vertex is a shorter distance than other possible paths. All right, so our first update. We're gonna update the table, data from B's neighbors. All right, so B can go, we could build the path from B to A for one. That's what I was forgetting. Do source. So we can get to B, get to A from B. It'll cost us a total path length of 1. So this is 0 plus 1 to get to B. Sorry, to get from B to A. We can also, so going down the table, all right, can B get to C. All right, just looking at its neighbors, look at the adjacency list. B to C, B 0 plus 2. We have F. F 0 plus 7. And then we have G for 1. Getting there from B. All right, so let's go ahead and update. Updating for the math. Same table, just keep running the addition step. And now we will get to our greedy option. Greedy step. Choose from the table a vertex to go to. The greedy aspect of this is to choose the vertex that would result in the shortest path being established. All right, so we can build a path from B to A for 1, B to C for 2, B to F for 7, and B to G for 1. Okay, the first smallest value wins. So we'll mark path to A as known, and then see where we can build from there. All right, so here's our updated state. We know the shortest distance that we can possibly get to A using B as our starting vertex is to go directly from B to A. And that will cost us 1 to get there. So now we are working with A as our source vertex. And it has edges out for us to consider. All right, so let's go down our table. From A, we can get to E and F. So right now, right, we could get to E from A, and that distance for our total cost path length will be the 1 that it cost to get to A, to start off with, plus an additional 4 for the transition from A to E. All right, so there's our potential path. that we're going to possibly build to. And then we have our potential path. Build here. This time we already have data for F. So when we get to F, we see that we already have a path. It's not the shortest path, so we can build it up. So we have a way to get here for 7, or alternatively, B could go to A for 1, then A can go here for an additional 3. Since 1 plus 3 is an improvement, we will take that improvement and we will replace the way that we get to F previously from B to now become A. And those are our 2 edges. So those are the 2 records that we will update in the table. Bold that to show that that was a state change. And we have thrown away the edge to B. And we will simplify our math here. And we're now throwing away this edge information has been discarded. No longer relevant. Right, because it's no longer in the table. We overwrote that data. Now we'll do our greedy step amongst the paths that we can build. Right, so we can build a path for any of these 4, and you can see the one that we didn't take last time because we had a tie previously. Now that's going to be the one we take. Building a path to G as it is the shortest path we can build. So we'll mark G's path as known shortest. Yeah, the numbers are the weights. All right, so we call those the weights. That could be a distance. 1 second here. Uh, okay. Well, managed to click on the wrong extra window over there. My address. You know where I live. All right. And you can watch the replay to see what I ordered. Let's see. Where were we here? All right. Building path G. So building a path to G. That will mark this as true. And then we'll look at G. So G is where we're building up. There's just one edge out of here that we have not yet previously worked with. So we're only processing new edge data because old edge data would only be a back path to an existing known path. So we have an alternative here. We could go to C. Right, we could go to C from G instead of B, but it already costs us 1 to get to G. And then an additional 3. So this is not an improvement. Since it's not an improvement, it's not going to update the table. So we will throw this edge away. All right, so G is tossed. And the data that we learned from G, so we'll be greedy again. Choose amongst our false paths that we can build to, right? We can't choose D or H because we don't know how to get there yet. But we do have data for C, E, and F. We'll take the shortest one, our greedy choice. C at a cost of 2. Copy my table. Previous one bold is what we had chosen before, and now we're going to C. All right, so we're at C. Tells us about one edge out. We had no information there previously, so the update will be straightforward. We can get to D from C, and it cost us 2 to get to C to start, and it'll be an additional 1 to go along there. No other edges to process. So we had chosen C, which I forgot to mark true. Which means I can come over here, mark it true. All right. Potential paths. So we have now 3, 4, and 5 as our options. All right. 3 is the shortest. So we're in D. Tells us about H. So we can get to H from C. All right, we're getting there from D. D had a cost of 3 to get there. So I have a 3 here, plus additional cost. Get from D to H at a cost of 2. And that was a replacement of no data before. All right, so we had gone to D. I'll mark that bold. State change. And simplify our data. All right, so we have 3 possible paths, a 5, 4, and a 5. So we will take F. All right, so we still have E, F, and G. All right, we know about possible paths to them, but we have not determined shortest paths. But since all the edges have been processed in the graph at this point in time, there won't be any shorter paths if I added some extra edges here that were really, really small. Like if I added a 1 here, then we would have had more data to process. But at this point, we're just going to be marking trues. All right, so we'll mark F is true. No new information. To set the table, the first 5 is E. So we'll mark that as true. Set that as bold. And then lastly, H is in here. And so we know what the shortest paths costs are, and we also know how to get there from the table. Right, so if I want to know how to get to G, come to the table, and see that the distance is 1, and we go there directly from B. I want to know how to get to F. You can see the distance is 4, and I got there via A, so I can go to A, and get to A via B. So we can see what the paths are, and how much it costs to get there. And it doesn't matter the order that you list the columns in the table. So we have where we're trying to get, how we got there, as the part that we'll be filling out based on our source vertex. All right, questions about Dexter's algorithm here? All right, let's do it again with a different origin. And I'll go partway through it. I'll let you finish. So starting at C, build out table. All right. So C, Oh, I was hoping it was going to toggle for me. Oh well. This is our source vertex. Distance is 0. Known true. I'll leave the rest blank at the moment. All right, so C. We have 3 options here. 3 edges to process. All right. B, 2, D, and G. D's for 1 and G's for 3. All right, so we'll take our first one. That's closest. And we'll go there. And that tells us about H. All right, so this path is known. And now we have H for 2 more. So we get H from D for 3. And then we'll do our one more operation here. We'll do a couple more here. All right, so we have options for 2 versus 3. So we'll take our 2, build our path. Build our path out. C can go to B or 2, and that will tell us about additional edges. All right, so we need to process these 3 edges against the table to see if we have improvements. All right, so B can get to G for 1, but that's the same as we have now because we have 3 versus 2 plus 1, so there's not an improvement, so we'll leave it alone. We can get to F from B for 9. So that's new information, and we can get to A from B for 3. All right. All right, so I'll let you solve remainder and post on Discord what you got. Grab our image so we can see what we've built out so far. All right, any questions about anything we talked about tonight?
Professor, I sent you a message before break.
Okay. Let's see. The GVE?
No, it was more of I was just wondering if test 2 is fully graded.
Oh, test 2. Yeah, test 2 should be fully graded. Were there any auto grader issues we needed for that one? I don't think there were there?
Well, I
Yeah,
know
test.
that you were saying one of the questions was going to be corrected
That's possible. I forgot
because there was
that.
an error.
Yeah. Which one
And
was
then I
that?
wasn't sure if the free response was graded or not
Well, it should show. Let's see.
because we can't see our grades, like what we got right or wrong.
I haven't released it. Yeah, so let me release that. Okay. You can release that, and then we'll look at the practice test.
Yeah, because I think one of the questions you said it was like, are there any errors or what errors are there, if any, on which line, etc. It was one of those questions, and the correct answer was 0, but you had put 3, but that
No, but
was a mistake.
yeah, but the key was correct, I believe. The key had 0 in it,
Okay.
so I just put the wrong answer when I was going over the test.
Hmm.
Um, Must be looking at the wrong test here. Let me get to the right test. Thought I had released it before we went over the test, but don't. No, yeah, test two's not restricted. You should be able to see it. Let me go see what it looks like.
Yeah, because I think even for test one, it won't show up. I don't know why.
Oh, I could have swore I took test two as a test student here. Am I in the wrong? Am I in the wrong class? Let's check.
Oh,
All
I just
right.
saw it was changed. Sorry. I hadn't checked it since this morning.
Well, it should have been available since we went over it last week.
Hmm. Yeah, I mean, at least last night I didn't see it had been
Well,
updated. So,
it wasn't graded until last night.
oh,
Yeah, I didn't finish grade. I created program two and the test last night. So yeah,
um, but but yeah,
should,
I just wanted to make sure that at least that question that you were talking about was like there wasn't a glitch on it or something.
I don't think there were any glitches. The only glitch was me when I went over it.
Got it. Okay. I just wanted to make sure.
Yeah. All right. When can I do the test input output for project three? Let me make a note on that one. Try to get that tonight. All right. Practice three for test three. Right. So test three is all about trees. So some of it be the terminology. What's height? What is level? What's depth? Things along those lines. We've got our n- ary trees, binary tree, which is our specific type of n-ary tree. It's a two- ary tree. Heaps, which are binary trees. Yeah, perfect. Heap property and shape property. Binary search trees, AVL trees, all fun stuff. So let's go ahead and exit the preview and go into the. Oh, a minute. All right. No. Do. Practice test. All right. So tree building. Tree building will definitely be a common theme on this one. When you're building the tree, you're building them in the order that they're presented to you. So our first tree is 27, 7. Then we add 42 along into it because we build from the leaves. 19 comes along, pushes 27 up. Then 24 adds into the party. They're basically asking how many. 42? Yeah, sorry, 49. 9. That's some terrible correction there. Let me grab an eraser. 9. All right, 24 gets added, less than 27. Find a leaf, drop it in. 39's up next. They're gonna add 71 wants to go over here. There's no space for it, so 49 will push out. We have our 1924 node. And 39 sticks where it was. 71 dropped into a new node. 88. And then 45. So 27 and 49 are in the root. Other ways this question can be asked: what are the two values in the first node and the second level? Right? Or I could ask this exact same question: what are the two values in the first level of the tree? Right? Remember, the first level of the tree is the first level. Whether we number this as level 0 or level 1, calling it first is unambiguous. It's the first level. Second level, that type of thing. Questions on our B tree? I'll take a look at how many questions are in the previous version of the test, so I can tell you that answer after we go over this. The root is in the first level, yes. The root is the first level. Why do you create a third branch? Because the second child split. The second leaf split of the root node, and that caused a third leaf to form and be associated with the root now having two values. Remember, a non-leaf node will have either 2 or 3 children. And if there are 2 data points in a node that's not a leaf, then that means there are 3 children. All right, our AVL tree, 35 balanced. 49, still balanced. 22, still balanced. 27, still balanced. 64, still balanced. And 41. All right, so the answer would be none of these. If we come along here and added 29, then the answer would have been 22. All right, so we had one more value. 29 would be the alpha node, because this is the one that says I need to do a rotation. 27 would rotate, 29 would go up along with it, and then 22 would slide down. And then we would have a completely perfect tree at that point. All right, so that should be none of these. Build up by your search tree was on the third level. All right, so the answer will not be the first number, because this is the regular binary search tree. That is going to be the root. Won't be the second number, because that's going to be on the second level. But after that, could be anyone. Not 42. So we'll have 37 as our first third level item. 69. Next item. 19 is going to skip that level. 31 is going to skip that level. 88 is going to skip that level. And then 53 will bring itself onto the third level. All right, deleting. Often it's going to be easier if you draw the tree that this graph is. Where the root is the first value, the next two values are its children. Next two values, remember, 9, 6, 9, 6, and then 7, 8. Well, 39, 31 went down the tree. Right, it was less than 37 and then greater than 19, so it just kept going down. So it didn't end up on the third level. All right. Delete. Delete is always going to remove the root. All right, so the value in the root is going to go away. the value that is rightmost on the lowest level is falling out of the shape property of the heap, which states that the tree is going to build level by level from left to right. So if there aren't enough data points to completely fill a level, then the right side will be empty. So 8 wants to reinsert, but 8 is not the smallest of our three options. So 5 moves up, 6 moves up, then 8 takes its place. So we have 5, 6, 7, 9, 8, 7. So we'll have 5, 6, 7, 9, 8, 7 as our heap after we're done here. Before I get erase happy, any questions on this one? Yes, this is a min heap. The smallest value is always at the root. And that's true for all of the subtrees as well. All right, build a max heap. All right, so we have 17, 12, 24. We'll push 17 out. And then 28 will work its way up. So 28 tried to go here. So 12 slid down. Then 24 after that. 23 comes along. 21 will cause 17 to move down. The rest of the tree is unchanged. 21. So next up we have 5. Then 20. And 18, 22, and 6. Fourth level, so first, second, third, fourth. So 6, 22, 18, and 12. Assuming I didn't make any mistakes along the way. You might want to bring a pencil and paper. Scratch paper to test 3 so you can start drawing out trees on your desk. Seems like we have no questions here, so we'll move along. All right, in order traversal. Again, draw the tree out. Be easier, unless you like doing 2i plus 1, 2i plus 2 math. All right, 44 is the root. 31, 69 is children. Got an empty subtree there. And then we have 41. Of course, scrolling off the side of the screen. 5 and 6. And we have 75 here. I gotta see if I can fix this. Horizontal scrolling is just bad. For a max heap, the larger values accumulate upwards. Left, right is completely irrelevant. It may just so happen that they accumulated on the left-hand side here just because the order in which they came. So if I change the question by taking these 3 out of here and then slide them to the end, corresponding tree would be entirely different. Not entirely different, but different. Oh, we can build another. We can build the heap again. After we finish going over number 6. Okay, so which traversal? In order traversal. All right, so this is a binary search tree, so in order traversal would just be 31, 41, 44, 69, 75. Otherwise, if we were to do this, right, first thing we do is go left. Go left, there's nowhere to go there, then we would output 31. Come to the tree, go left, nothing there, output 41. Go right, come back up, back to 44. Output that, 69, has no left. Go to 75, no left, output 75. No right, back up to the root. So the root is, right, 1 based, so 3, it's the third output. Yeah, we can go over big annotations as well. All right, let's see if I messed up. All right, didn't make any mistakes, so that's good. All right, so building the max heap. So first up, we have 17 becomes the root, and then 12 builds underneath that. 24 will push 17 down. Right, because 24 tried to insert where 17 is now, but it found its parent to be lesser, and that's not acceptable in the max heap, so they had to go ahead and pull 17 down and take its place. 28, right, 28's trying to go here, wants to build itself into this location in the tree, but then it checks its parent and finds that that is not going to work out. So 12 will move down, 28 move up. And it's going to check its parent again and find that that's not going to work out. So 24 will move down and 28 will move up. All right, 23 comes along, smaller than its parents. We're good. Then 21 comes along, and that's not going to work with its parent relationship. So it is going to move up by pulling 17 down. It's going to check its parent and see 28's above it. So it's going to go ahead and stop there. Then 5 fills in. It's less than. Try that again. It's less than its parent, so it'll stop right there. Next up, 20. 20 comes, but it's not happy with the relationship with its parent. So 20 moves up, allowing 12 to go down. 20 checks its parent, and it's good to go. Then 18 comes. It's less than 20, so it stops. 22, it's less than 23, and 6 is less than 23. So let's see if I can squeeze these in here into our drawing. 18, 22, and 6. And so every path that we can build is on a non-ascending. So it's 28, 24, 20. Or we can see that 21 is larger than many of the values over here in the left subtree. Same thing is true with 17. It's larger than a couple of the values in the left subtree. The smallest value happens to be over here. Smallest value could be anywhere in the tree other than the root or the root of anything because this is a max heap. All right, so say we were to build similar tree, but swap the order of our values. Oh, whatever, 623. It's fine. Well, no. Might as well keep them all the same. All right, we'll build the tree again. First value starts as the root. And then 12. Let's make the tree a little bit bigger to start. Comes along, fits in just fine. Does not change where things are going. 24 as before. It's not going to accept a smaller parent. So it goes up. 28. Moving in next. Not going to accept the smaller parent. 12 will move down, allowing 28 to go up. Who's not going to accept a smaller parent? 28 moves up again. All right. Now here we had a change in the order, so we're going to diverge. 20 comes along, it will stay because it's less than 24. And 18. 18 is greater than its parent, so it will not sit. Excuse me. All right. Oh, how did I manage to grab that? Oh, that's just not cool. Out of the way box. 17, 18 checks its parent, and it'll stop there. So next up's 22. 22 will not stay because its parent is lesser. 18 will make way for 22. 22 will check its parent. And it's greater, so it'll go ahead and stop, right? No one's going to supplant 28. That's the largest value in our complete set of data. So we're never going to have anything bubble above that. 6 comes along. Less than 12, so it stays. 23. Not be the same story. So it's going to move up. Part of the reason why larger values are ending up on the left is just because we're filling from left to right. So that's the opportunity for movement to come along. And there's just going to be, there are more values on the left. So since there are more values on the left, larger values are going to push their way up because they're not, for the most part, going to sit in the lowest levels. And do note by level, right, we have 22 and 18, which are larger than values in the level above, but not on the same path towards the root. Yeah, heaps are array-based. They need to be array-based so we can quickly find where the next value is going. The next value is going where what the count is. Right, so the count is basically this next position in the array. And we'll move along. So 21's next. Our new data set. Not happy with its parent being above it. And thought I'd figured out how this selecting pattern works. Must be an age component or something. All right, so fine. 6 moving. So we can make some space here. Apparently I should be copy pasting these so I can have the right size. 21 moved up. Sliding 20 down. And then we get a 5. And it will sit. So this time, the 4 lowest values do happen to be on the lowest level, but it's just all dependent on the data. All right, so a heap is balanced. So whenever we have a balanced tree, and the operation that we're doing is concerning itself with a single branch, right? So the next insert that would happen would go down this branch to a new value that would be added. Finding that position's constant time, because we're just looking at the count. That's the index that we want to insert. We have to check our way back up to the root. If I try to add 40 in here, it's going to compare to the parent. 40 is going to move up. Compare to the parent, move up. Compare to the parent, move up. So the furthest it has to go is directly proportional to the height. It may not have to go up at all, just like 5 didn't. Just one test and done. The insert happened in constant time. But the average is going to be logarithmic, and the big O will be logarithmic. And of course, big O is always worst case, right? Unless the question says, what's the average big O? It just says, what's the big O of this algorithm? We're talking about the worst case. Yes, the next value that gets added would test itself against 17. They would, cut its index in half. After, I think, subtracting 1, I forgot to look at the math every time because that's stuff I don't want to memorize. And so the next 2 would look at 17, or at least this index in the tree as a parent. That value could be 22 after the next insert. Questions for the min heap. The method would be similar, except, yeah, the only difference between min heap and max heap is the orientation of the operator. The relational operator that's comparing, is it a less than, or is it a greater than? Everything else is the same. And also, don't forget, duplicate values are not a problem for heaps. Yeah, so let me go see how many questions are on the last semester's version of the test. All right, okay. See how many questions we have. So the number of questions typically does not change much between semesters. Getting there. Okay. We have still 23 questions. There's multiple choice. All right. Big O questions, big O, 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 big O. And then now we're talking about tree height, which trees are array based. Build a tree, build a tree, build a tree, build a tree. Do a traversal. Do another traversal. Build a tree. And then what types of trees could these be? Yeah, so it's only like three questions smaller than before. And the code questions very much like, I can add that. And the practice test. Let's see. We're doing tree stuff just like the program 3. So let me add. I want you to forget about the code. There is code on the test. All right. All right, and reorder. Order node start and to the following tree. All right, so we have a node. Oh boy. Silly paragraphs wanting white space. What a terrible way to do things. Terrible way. Next, carriage returns. Public. Node star left, star right. And data. And then we'll have our prototype. Pre-order. And we don't need prototype. Oh yes, node star prototype for our function. And then we would have the helper. We would just, I'm getting ahead of myself here. Into the next class. Tree class. Right, node star root. And our helper function, which would just go ahead and call reorder. All right, other function code as needed, other prototypes as needed. And get height. All right, same idea. Except of course height is no longer going to be returned. Our void type will want to return data. All right, so they're not big functions. We're the trees. All right, so it'd be very much like program 3. All right, the other questions are about things along these lines. Yeah, big O. Several big O notation questions. Most big O answers are going to be either linear or log. For trees, it's not always the case, but those would be the two most common answers. And if the tree is not balanced, linear is possibly the answer. Remember, let's see. This is a binary search tree. Yes, big O notation defaults to worst case. And here's our lovely binary search tree. So we try to search for a 3. We went through 4 nodes to find the answer, which is equal to the number of data points in the tree. Whether it's array-based or link-based, doesn't much matter if this is the tree. We're in sad town because it's basically just a linked list. And typically there's space between terms. Space is for the parentheses, which should just be one set of parentheses if it's a free answer. But at this point, we're just multiple choice because we have pretty much standard It was free answer previously because some people would make the early mistake of trying to add numbers in the big notation. There is no big O 4n or 10n or 30n, right? It is simply n. So the tests from now on won't bother with free answer or the notation. It'll be just one of the standard classes. It's big O1. Right, let me add, so you don't have to worry about that. What is the big O? We're inserting to a binary search tree. All right, so we'll have big O1, big O log n, and they will be in time order. Big O n times n, and the infamous none of the above, which statistically people don't like to choose even when it is the answer for some reason. I don't know why that is, but it is one of those things. Of course, I forgot to select the correct answer. Let's select the correct answer. I'll get fewer questions that way. Oh yeah, I don't think trees aren't a heavily used data structure as sorting things and searching for things. That is very, very common thing to do. Trees are far less common, right? The only place that I know commonly uses are database indexes, where we talked about B trees and heaps, binary heaps being used for our indexes there because that helps us navigate to the data we're trying to get to much quicker than not having those indices. We'll often use trees in the graphs section because they're specialized graphs. So we'll make use of some trees over there. So when that gets relevant, we'll talk about that as well. But yeah, there's the probably I'm sure there's probably a big cheat sheet. Does have on tree stuff on there? I don't remember. I remember it has sorts and it has various things in here. Yeah, there's trees. B tree, right? Login, 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 log, 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 log. So for the space complexity, right? Because it's balanced, right? AVL tree, same story, balanced. If you're balanced, you can get those log times, but otherwise, binary search trees, right? No balance. So you can basically infer which trees are not balanced just by looking at the annotations here. Contributors. All right. Okay. That'll bring us a balance of time for lab. So next week we'll go over code for the adjacency list, which is basically I'll remember. Don't remember if I have saved that or not. Did I will steal that code. I should probably save it so I can just steal it, save some time. Run through, do Sunday. Could be. Could be. Let's see. That requires me to remember. And remembering is a lot of work, especially data that becomes no longer relevant in a week or two. All right, program 3, do the 22nd. Yes, you have 6 days still to work on that one. Code for this one's really not terribly hard. Once you've gotten down how a traversal works, basically you can adapt the traversal to half of these other functions and adjust it. So on the sample input output, I'm going to create a test project on online DGB here. It's basically what I use to test your code to see if it works. So I will pass along a link to this, and I'll open up this one. You can test against it so you can see if it's giving the expected output. The lowest weight function, it's just a traversal. You have to look at every node in the tree. Right? So you start the root. My lowest weight is the root. Then until I can find someone smaller. Right? So here, let's build a tree. Weight and string name. I guess I should include the string namespace. String. And node star left. Node star right. EST. Public. Star root. Constructor. And add function. We got int weight. String name. Node star n equals node. And name equals n and weight equals w. Root at if root equals 0, whatever. Then root is n and we're done. Otherwise, star temp equals root. And we will just loop until we break out. If so we're doing name, right? If name is less than temp name, we're gonna branch left. Otherwise, else if temp name, lost my arrow. Are we testing out? Yeah, I can show you how to do it in a minute. We can, yeah, we'll just test this. All right, else if temp name less than, then we're going right. Else, just break out a loop because no dupes. No dupes. All right, so if temp left is null, then we can go ahead and attach our node and be done with it. Otherwise, temp right is null. We can attach and be done with it. And now we have lightest, which we'll call lightest the root, assuming there's a root. If root, call lightest. Otherwise, empty tree. Right. Good to get in the habit to not trust the user to call lightest after they started building nodes, especially if you have a menu. And will definitely not work out so well. All right, so in lightest, nodes to our root. All right, so we have our lightest equals root weight. Now we have int left equals, and we'll do int left equals light, int right equals light if root left go get. Yeah, that's fine. That should cover us for our base case. Left equals lightest. Left. Test code, just make sure it works. If right. Right equals lightest. Right. Right, so if left is less than light, update light equal left. And if right is less than left, no, not left, no semicolon there. Left is less than light, then light equals right, and we will return light. Okay, so we have the empty case. We will just spit out no tree. Then we'll have a one node case, the root. So whoever's in the root is passed along to our function. We'll grab the weight, 5, 10, 100, whatever the weight is. So we'll have the weight in there. So it's 5. Then the left is 5 and the right is 5. If there's a left subtree, go ask what it is over there. And it should come back and return if it's a number. If that number is lighter than, we'll update it. All right, so let's do some tests in here. Fact. Let's see. So I've got my AST tree. String name, weight. I really should update the prompt so we can make this all automated. Well, do wow 1 second here. All right, so getter name. You don't necessarily have to have two functions, but one's gonna be, you want it to be recursive. So it tends to be easier if you have a helper function. So wait. And tree add. They have name and weight. Weight and name. All right. Weight name. And if name equals 1, we'll stop. That's not actually what the prompt says. Prompt says for 15 people, but I want to be able to do more test cases. Entry add and see out. Smallest. All right. What? This got mad that I can't type? Should autocorrect for the me. That's just terrible, terrible autocorrection. I forgot my semicolon. My daily is when I'm writing good C sharp, and we don't do the silly semicolon over there. Shadows a parameter. It totally does. Totally does. Let's fix the bugs. Indeed. Guess I've changed the wrong one. Name. And that's good. All right. No return statement function. That's fine. Bob, 10. Smallest is 10. All right. Tony, 20, still 10. Tina, 5. Now it's saying 5. So far, so good. Now, on to testing things. All right, where did I do it? Here we are. Build. I guess I have it here. See how good the links work and all that other stuff. I'm sure I'll have to fix this. Yeah, came out pretty good, actually. I'm surprised. All right, so add a test case. One node. Bob 10, -1. And the output expected here will be like for a 10. Right, so this isn't what it would be for the program. I'll have to build that out first. Not what I meant to do. I meant to copy my code. So I will send a link to this, right? And you can run and debug like normal, right? Bob 10, smallest is 10 type thing, but you can also click the test button. And clicking the test button, now I'm still running. I need to stop running. Clicking the test button when I'm not running will run it through and it'll show your output after feeding this input in, and this was the output. It's not very intelligent on the actual checking the values here, but I will show you what the orders should be for the 15 people. We do have, yeah, for what would be for 15 people. So let me go ahead and invite, put it in the chat, and I'll make a post on that. In case you want to test your code. Test your code. Sign up here. Choose Irvine. Play college. In the drop down when you get to that part. Yeah, after nearly 20 years, I'm finally getting a little bit more automation into things here. my stuff that I have on my computer for downloading, compiling, and running code and having it testing against the test suite, but there's so much variation in the way that people do their output. It's not exactly the most effective mechanism. So I'm testing this out, see how well it goes. I was going to use Replit, but apparently Replit's so slow that I'm shying away from that. So we'll see how well this works. It is super particular about what the output is for its comparison, even in loose testing mode. So it's not the greatest. Anyways, any other questions? All right.